In this video, we're going to solve another second order circuit. Now we are being asked to find V0, the voltage across that resistor in our circuit. But before we can try to write a differential equation, let's go ahead and see what happens after the switch goes. So switch moves to the right. So we have our inductor here, we have our capacitor and resistor. So this is going to be an RLC series circuit again. Now we know for RLC series that the differential equation is x double prime plus r over lx prime plus 1 over lcx equals some constant. In this case, we're trying to find that V0, but you know what? We might as well just, since I is the best variable to solve for in an RLC series circuit, we might as well go ahead and find out what I is using our standard formula here, knowing that it's 0 for just the current, and then we can go ahead and multiply by the resistance there to find the voltage. So in this case here, my R is 2, my L is 1/2, so R over L is going to be 4. And then we have my L times my C is 1/2 times 2/3 is 1/3. 1 over that becomes 3I. We then get our auxiliary equation, s squared plus 4s plus 3 equals 0. We can factor that, s plus 3, s plus 1. We get -3 and -1 here, which means my solution is going to be k1 e to the -3t plus k2 e to the -t. Now we need to go ahead and look at what happens right before the switch happens to get some initial conditions. So at 0 minus, the inductor becomes a short, capacitor becomes an open. We have our resistance here. Then we have our current source, 2 amps. So because of the open circuit, the 2 amps is going to go all through here. So our initial current through the inductor is 2 amps. Now we can see, since this is a short, the voltage here is going to be 0 volts. However, since we haven't opened the other side, there's going to be no current across the resistor, which means my initial voltage across the capacitor is also 0. So Vc of 0 is 0 volts. So now we need to go ahead and write out what my I of 0 is. Now there is going to be one issue here that we're going to have to be careful about. In my t equals 0 minus picture, the current is coming down here through the inductor. However, if I use that as my true I of t, then when I get over the resistor, I'm entering the negative side, and it won't be V equals IR, it'll be V equals negative IR. So just keep that in mind here, that it's going to be negative IR for the V0 of t. So if I plug in 0 into my formula for I of t, I get K1 plus K2, and we know the initial value is 2 there. Then, as we've seen many times, we're going to go ahead and take our derivative here. -3 k1 e to the -3t minus k2 e to the -t. And I prime of 0 then is -3 k1 minus k2. And we know that the reason why we do this is because we have an inductor, and we know that for an inductor, the voltage is L times the derivative of the current. So if you look at right after the switch happens, we have this resistance here, 2 ohms. We know there's 2 amps going through right after the switch happens. So that means there's a 6 volt drop across the resistor. We know that initially the capacitor had a 0 volt drop on it. So it's not going to change right after the switch happens. So that means the voltage across the inductor, in order to counteract the resistor drop there, it's going to have to be 6 volts. Actually, sorry, because our current's going the opposite way. All right, it's going to be negative 6 volts. Okay, so that means that, I prime of t is 1 over L VL. So I prime of 0 is negative 3k1 minus k2. It's 1 over L, so 1 over half, 2 times the voltage there is negative 6, means negative 12. We need to use these two equations to solve for k1 and k2. If I go ahead and add down, the k2's cancel. We get negative 2, k1 is negative 10, k1 is 5. That means k2 is negative 3. So we get I of t is 5 e to the minus 3t minus 3 e to the minus t. And then finally, as I said, we're going to use Ohm's law, noticing that it should be negative IR. R is 2, so negative 2 is going to be a negative 10 e to the negative 3t plus 6 e to the negative t, and this is measured in volts. So that gives us our solution for the voltage across the resistor in this circuit.